Okay, so we have now learned about the types of reactions that we're going to talk about in this class. From here, of course, we move into specific reactions that we're going to do. The first one we're going to do is the simplest possible acid-base substitution, and that is where we transfer a hydrogen from an acid to a base, right? And so we're going to break the sigma bond that connects the hydrogen to whatever our acid is, and we're going to make a sigma bond between our base and that same hydrogen atom. So we're going to do that today. We'll run through this really quick. We'll do some examples. You'll see what they are, and of course, we're going to focus on, remember what the main skill of acid-base reactions is. The focus is going to be on identifying the acid, identifying the base, and kind of getting familiar with what those roles could be. So here we go. All right, acids and bases. We're going to use the Lewis acid, Lewis base definition that we briefly touched on in the previous video, right? And that is a Lewis acid. Actually, you know what? We probably shouldn't be abbreviating this early on in the video. A Lewis acid is something that accepts electrons. Right? And so this means that this is going to be where arrows end, right? So when we draw our arrows are going to point to where the electrons end up, and so that's going to be what accepts the electrons. And so whenever we draw a mechanism or draw the flow of electrons in a reaction, where our arrows are always going to point toward the acid. So in that case, you'll never guess what Lewis bases do, right? Lewis bases are the electron donators. Lewis base donates electrons, and this is where our arrows begin. Right? So when we talked about resonance, we said, well, where are places that we can move electrons around? Where are the places that we can start? And really, we came up with two options, right? We had two possibilities for where we can start. So this is where in class, I would stop and say, okay, so what are the electron movements that are allowed in resonance structures? And you all would say, lone pair to pi bond, pi bond to pi bond, pi bond to lone pair, right? Those three things. And notice that in all those cases, we start from a lone pair or we start from a pi bond. Lewis bases are no different, right? If that's where our electrons start, this is where our arrows begin, we're generally going to associate lone pairs and pi bonds with the idea of being a Lewis base, okay? So in almost all substitution reactions, we're going to be identifying what is the Lewis acid, what is the Lewis base, right? In fact, we give these special names when we're talking about substitution reactions, actually in a lot of different organic reactions. So we'll put one more name over here. A Lewis acid is the same thing as an electrophile, right? It accepts electrons, it loves electrons, so it's an electrophile. And a Lewis base is called a nucleophile, right? This is the thing that donates electrons, and so it gives them away. Okay, so nucleophile, electrophile are the same thing as acid-base when we use the Lewis acid, Lewis base definitions. Okay, we're going to look at, let's look at a reaction of sulfuric acid, H2SO4, and water, H2O. And I'm going to give you the products in this case because that's going to be important as well. So the products are going to be HSO4 minus and H3O plus. Okay. So you'll notice, of course, we have two starting materials, we have two products. The big difference here is an H plus has been transferred from H2SO4, right? The starting material had H2SO4. In the product, it has lost one hydrogen atom, has lost one H plus to H2O. right? And so H2O in the starting material started with as a neutral compound, but has picked up H plus when it goes to the products. And so an H plus is being transferred from one to the other. This is a substitution reaction. This is a very specific kind of substitution reaction that we call a Bronsted-Lowry acid-base reaction. Right? So Bronsted-Lowry acid-base reactions always involve the transfer of H plus. Right? And these things are everywhere. Right? We're going to use this reaction so many times that we're going to stop writing it down, basically. We're just going to say, oh yeah, H plus gets added here, or H plus gets transferred here. We're going to kind of hand wave our way and say, yeah, everybody recognizes this, right? Now, of course, we're not doing that right now because not everybody recognizes it, because this is the first time that we're really digging into it, but we're going to use this one a lot. Right, so anytime we transfer H plus from one compound to the next, right, this is always going to be a Bronsted acid-base reaction. The Bronsted acid-base reaction is so often used for a couple of reasons. One, it's just really, really fast. This is one of the fastest reactions out there. It's not the fastest reaction that we know of in organic chemistry, but it is right up there. Right, and two, it gets used a lot because it's an equilibrium process, right? It varies. So if you remember back to Gen Chem 2, when you guys had to do all your KEQs and KAs and KBs and titrations and all that other kind of stuff, all of that was based on this idea of the Bronsted acid-base reaction. And so we really understand it really well because we've done all this math already on it in previous courses, and it's a very fast reaction that we know is easy to occur. And so if we get a handle on what this reaction is, what we can do with it, we're going to get to use it a lot. And so it's going to be a really useful one for us in this thing. I want to just define a couple of terms, and that'll kind of do it for this video, right? So first of all, if we want to identify the acid and the base in this case, right, of course, sulfuric acid is the acid. That's why acid is right there in the name. That makes water the base in an acid-base reaction like this, right? And so you'll notice, of course, that the acid is the thing that's going to give away the H plus, right? So the acid is going to gain some electrons because it's going from neutral to negative, whereas the base is going to give electrons away because it's going from neutral to positive. Now I drew equilibrium arrows here in the middle, and that means that this reaction can go back the other way. And so we can also think of the same way, right? If this compound picks up H+, it goes from being HSO4- to being H2SO4. And so in the reverse reaction, if we considered these two compounds over here as our starting materials, this would be a base, and this would be an acid. Right? Now, of course, these two things are related to each other. H2SO4, anytime sulfuric acid reacts as an acid, you'll produce this base as the product, HSO4-. And so we call this a conjugate base. Right? So we have a conjugate base here. HSO4- is the conjugate base of H2SO4. H3O+ is the conjugate acid of H2O. And all that means is that if you do an acid-base reaction with H2O as your base, you will always produce H3O+ as your conjugate acid, right? These two, the H2O and the H3O+, are always paired together, right? One on each side of your reaction. Same thing with H2SO4 and HSO4-. They're always going to be paired together on each side of the reaction. One will be the acid, sulfuric acid, and one will be the conjugate base. So, and like I said, these reactions are equilibria, and so they can kind of go both directions. Okay, that's our very first example of a Bronsted acid-base reaction. The next video, we'll have a whole bunch more, and we'll actually draw some arrows and see how the electrons are flowing and why we call things Lewis bases when we say that they donate electrons and all that kind of stuff. So we'll kind of close that loop in the next video. So click on that one next.